All right, so it looks like we have a cubic function here. We need to find some characteristics for it and then also make a graph for it. So yesterday we were talking about how to figure out the inflection point, right? And the typical shape for a cubic graph. So let's put that to work. So just to write here, I'm going to write the generic equation for a cubic function. So like we talked about yesterday. And if you need to look in your journals, this one's going to be journal. Sorry, that should be a 2. Let me fix that. So that is going to be journal 27, if you want to look back on your notes. So here's your generic equation, and whenever the inside the parentheses is negative, just like parabolas, that means it's going to the right. And whenever it's a positive, it's going to the left. So in this case, we can see that there is a negative sign in here. So we have a horizontal shift going to the right because it's negative 3 units. So we always start at the origin. So here is the origin, and we have to move 3 units to the right. So there is my point there. I'm going to plot that on my graph. Plotted. And I have to figure out what's the coordinate for that point there. So it looks like that's at 3, 0. So I'm going to put my coordinate or write my coordinate right there. So 3, 0. And now let's see what I need to grab. So I have 1 point on this graph. Let's find the y-intercept. So finding the y-intercept, remember, what is our x value for all y-intercepts? Well, that's 0. So if x is equal to 0, then I need to plug in this 0 into this equation to find my y, because that's what I'm missing here. So my x is equal to 0. I need to find my y. So I'm going to plug in the 0 for x and then solve for my y. So on here, that's going to be 0 minus 3 cubed. And we're using order of operations, so PEMDAS. So we have to work inside the parentheses first. So 0 minus 3, that's going to give me negative 3. And then I have to cube it. Well, negative 3 times negative 3 gives me positive 9. 9 times negative 3 gives me negative 27. So it looks like my y value for this case is negative 27, so I need to put that value here. And so negative 27. All right. So let's actually get to plotting. Now, the y-intercept is really... sorry, that's the wrong button. Where's my... There we go. So the y-intercept is really far down, right? I'm not going to plot the y-intercept, but I still need more points on this graph to draw my cubic function. So for a cubic function, you need actually 3 points, just like the parabola. So we have 1 point on here. It's the inflection point. So we need 2 more. Okay, so how do we do this? We start by looking at our inflection point, and we're going to choose an x value that's close to this inflection point. So in other words, my inflection point's at 3, right? So if I choose an x value that's really close, that's either going to be 2 or 4, so basically 1 unit away. So I'm just going to choose x equals 4. Okay, so we choose an x value, so I'm going to choose x equals 4. And I need to figure out where does the cubic function hit when it's x equals 4. Well, in other words, I need to find my y. So to find y, I need to plug in this x value into this equation to find y. So I'm going to set that up. So 4 minus 3 cubed in this case. So if I work this out, well, 4 minus 3 gives me 1. If I cube that, I get 1, because 1 times 1 times 1 gives me 1. So when I write this out as a coordinate, that means at 4, my y value is at 1. So I'm going to plot that on my graph here. I'm going to use green to plot this. So 4, 1 is right here, right? And the beauty of cubic functions is that there is a symmetry. The only thing is that if you look at a cubic function, it's kind of like opposite in its symmetry. Like if you have a point, so if this is the inflection, if you have a point here, right? The other point that's symmetrical to it is in the opposite direction. So it's like this point went up and this point went down, but they're kind of like the same apart from the inflection point. So let's take a look at this inflection point here and the point that we just plotted. So it looks like it went up one and over one, right? So up one and to the right one. So we have to go opposite to find to plot our third point. So we have to go down one and over to the left and then plot our new point there. So I'm going to grab my marker again. Plot that. And now I have 3 points. So I can go ahead and draw my cubic function. So it looks like I go down this way and then I have to go up this way. So remember, cubic functions are typically down first and then up. And there we have it. We have a cubic function. I also want to point out, so you don't have to choose an x value to figure out one of the points first and then figure out the other point by going the opposite way. You can also just look at the equation here. So if we look at this equation, you want to first look at the x value and its slope in this case. So for this x, we can see that the slope for this x is, well, what's the number in front of this x? It's 1. So my slope here is 1, but we learned back in the first unit that anytime you have a whole number or just a number, you put it over 1 so that you can figure out the rise over run. So turns out when you are close to the the inflection point, you can use the slope to help figure out what your other 2 points are going to be to plot. And funny thing is, if this is 1 over 1, so from the inflection point, you would go up 1 and over 1. Well, isn't that the point we just plotted a moment ago? And so you would plot it there. Using the slope, again, you can go the opposite direction, so down 1, over 1, and plot it there. And it just so happens that that also gives you the 2 points that are next to the inflection point. So that's another way of finding your 2 points to plot for your cubic function is using the slope. Okay, now I do want to be wary of this. This is something we use that's close to the inflection point, and we're going to do some more practice problems with this. Now, domain and range, if you guys remember from yesterday, the domain and range for all cubic functions is all real numbers. Why? Well, because domain is talking about the x values. How far does this cubic function go left, and how far does it go right? So if you can see that this cubic function never stops pointing to the left and never stops pointing to the right. So in this case, we're going from negative infinity to positive infinity, so all real numbers. It also is always pointing down and up. So for the range, we're going from negative infinity. So y is going from negative infinity to positive infinity. So it's all real numbers again. And that's basically it.